In this video, we're going to talk about the convergence of Fourier series. So the key theorem that we're going to state is the following. If f and f prime are both piecewise continuous on the interval from negative L to positive L, then for any x in the open interval from negative L to positive L, the following is going to be true about what the Fourier series converges to. So the left-hand side of this equal sign is the Fourier series for my function f. And what this theorem says is that Fourier series is going to be equal to 1/2 of f of x plus added to f of x minus. So it's the average of f of x plus and f of x minus. So you might be wondering, wait, what are x plus and x minus? So this is notation from calculus involving limits. So recall that from calculus, so what this notation means is when I write f of x plus, that's the limit as we approach x from the right. So more specifically, it's the limit as h approaches 0 from the right-hand side of f of x plus h. So I am going to review this a little bit below after I state the theorem with the picture. Okay, and then similarly, f of x with this negative sign written in the exponent is the limit as we approach x from the left-hand side. So specifically, that's the limit as h goes to 0 from the left of this should say f of x plus h. All right. And it turns out that when x is at the endpoints, so either when it's positive L or if it's negative L, the Fourier series will converge to 1/2 of this sum. So f of negative L with the plus, so that's the limit as we approach negative L from the right side, added to the limit as we approach positive L from the left side. Okay, so I want to introduce a little bit of terminology so I can refer to this whole thing without having to write down the whole formula. So this whole thing, I'm going to call this fs for Fourier series. It's the Fourier series of the function f of x. So I'm going to write that as a subscript. And this Fourier series is a function. It's a function of x. So this notation, I'm going to have this mean the Fourier series of the function f of x. So I'll be using that notation. Okay, so let's do a brief review of what these one-sided limits are. So recall that if I have a picture like the following, so if I have a function f of x whose graph looks like this, then what is f of 1 with a plus? And what is f of 1 with this minus? So f of 1 with the plus means, well, what's the limit as x approaches 1 from the right-hand side? Okay, of f of x. So as we approach 1 from the right-hand side, that is this part of the graph. We're getting really, really close to 1 from the right-hand side. And as we do that, the y values get close to 0. As we approach 1 from the left-hand side, we are going along the graph this way. And as we do that, the y values get really, really close to 3. All right, so that is what this sort of one-sided limit notation meant. All right, so what are the key takeaways from this? So if x is an element of our closed interval from negative L to positive L, I'm going to sort of summarize what f will converge to depending on what the function looks like. So if our function f is continuous at x equals a, then it'll turn out that these one-sided limits are the same. And in that case, the whole thing will just become f of, f of a. Okay. When our function has a jump discontinuity at x equals a, the series converges to what our formula said, 1/2 f of a from the right plus f of a from the left. Okay, so in the special case when my function is continuous, this formula will simplify to just f of a. Okay, so in the third situation is, well, what if x is one of the endpoints? Then what the series converges to is it'll converge to 1/2 times f of the left endpoint, negative L, its limit from the right-hand side, plus f of the other endpoint, which was L, but its limit from the left. All right, so let's do an example. So here is our example. So I'm going to let f of x be this piecewise continuous function. So it's x squared if negative pi is less than x is less than 0, and it's 1 if 0 is less than x is less than pi. So we saw this piecewise function in the last video. In fact, in the last video, we actually determined the Fourier series for this. So now I want to answer the question, what does the Fourier series for this function converge to at these x values? All right, so before we answer this, I want to draw a picture. All right, so I want to draw a picture. So I'll draw my axes, so my x and my y axes. And now let's go ahead and draw the graph. So our graph, so on the left-hand side of 0, it looks like x squared. So there's an open circle at 0, 0, because x is not allowed to be equal to 0. Okay, so I'm drawing the x squared graph on the left-hand side of 0. So that'll look something like this. It'll look like the graph of x squared. And then I stop when I reach negative pi in terms of what x is. And because x is not allowed to be equal to negative pi, we put an open circle here. All right, so this is the point negative pi, comma, pi squared. And then on the right-hand side of 0, when x is greater than 0, the function value is 1. Okay, so I'm going to draw an open circle here, and this is the point 0, 1. There's an open circle there because x is not allowed to be equal to 0. If x was allowed to be equal to 0 here, then I would have had a closed circle. Okay, and then the function is just 1, so it's horizontal like this, until x reaches pi. And when x reaches pi, because there's no equal sign here, I put an open circle at that point. So this graph that I've just drawn in, this is the graph of our function f of x. Okay, so I've been sort of coloring this in just in black. So when I see this black graph here, that is the graph of f of x. Okay, so now let's start to answer the different parts of this question. So let's start with part A. So what is the Fourier series going to converge to at x equals 0? So I'm going to use my notation. So fs subscript f of x, and then I'm going to plug in 0. So let's remind ourselves, what did this mean? So this notation just means this is the Fourier series of the function f of x, and now we're evaluating this at 0. So what do we get if you plug 0 into the Fourier series? What is that going to converge to? So using our convergence theorem, it says that this is going to be 1/2 times f of 0 plus, so the limit as you approach 0 from the right, plus f of 0 negative. That means the limit as you approach 0 from the left-hand side. Okay, so what are these two limits? So as we approach 0 from the right in this graph, so 0 from the right, that is this side right here. We're approaching 0 from the right, and the y values are approaching 1. What about as you approach 0 from the left? As you approach 0 from the left, that is this part of the graph. So this part of the graph is approaching 0 from the left-hand side, and the y values there get closer and closer and closer to 0. All right, so what this ends up being is just 1/2. So when x equals 0, the y value that the Fourier series converges to is 1/2. So let's draw that in the graph. So 0, 1/2, that would be here. So notice that's sort of like the midpoint of where these sort of jumps are, sort of where this hole is and where that hole is, where these two circles are, where these breaks are in our functions pieces. So in orange here, I'm starting to write the Fourier series. So the Fourier series for f of x. All right, so now let's do part B. what is the Fourier series going to converge to at positive and negative pi? So what is it going to converge to at positive and negative pi? So these are endpoints. These are endpoints of our interval. And at the endpoints of our interval, we are going to get 1/2 times f of the left endpoint, negative pi, but we take its limit from the right-hand side. One of the reasons why we do it from the right-hand side is we only have the right-hand side of the function here. Like, we don't know what's happening to the left of negative pi. Okay, and then we add that to what is happening to pi, the other endpoint, but from the left-hand side. And we do it from the left-hand side because at pi, well, we know what's happening from the left, but there's nothing there to the right. Okay, so if we evaluate these, so we have 1/2. And the limit as you approach negative pi from the right, what was that y value? So the y value as we approach negative pi, as x approaches negative pi from the right, that was pi squared. And then as x approaches pi, but from the left, that's this part of the graph. So as you're getting closer and closer to pi, the y value is getting close to 1. So we end up with pi squared plus 1 over 2. All right, so let's box those answers. And let's draw in where this is on the graph. So pi squared plus 1 over 2. So pi squared plus 1 over 2 is sort of the average of this y value, the pi squared, and this y value. I guess technically I shouldn't actually say that one. Technically it's of this endpoint here, sorry, of pi 1. All right, so let's go ahead and underline its y value, which was 1. So the average of those is pi squared plus 1 over 2. So the average of those seems to be maybe somewhere here-ish. And if we draw those at each of the endpoints, our Fourier series at pi is going to converge here. And at negative pi as well, it's also going to converge to that same, let me draw that a little bit better, to that same y value. Okay, now let's answer the last part of this problem. Well, what is the Fourier series going to converge to at pi over 2? So, okay, I don't want to get too far ahead. So the thing about 5 pi over 2 is, notice that this is outside our interval that our function was defined on. It's outside the interval from negative pi to positive pi. Because we know what the Fourier series is going to converge to on that interval. The convergence theorem tells us. And remember, so the negative pi and the positive pi, they're the negative L and positive L here. So one thing that we saw in the demo, let me see if I can bring that up one more time. So in the last video, I showed you all this demo in Desmos. So we had the graph of our piecewise function, and I showed you an animation for what the Fourier series looks like if we add more and more terms into it. And so I'm just going to draw now the Fourier series when a equals 50. Actually, let's even make it larger. Let's make a just 100. Okay, so notice that the Fourier series doesn't just sort of occur where our piecewise function is. It sort of occurs outside of that as well. And notice that it sort of keeps repeating. It keeps repeating the same shape again and again and again, no matter how far out I go. So Desmos is just sort of displaying it a little bit slowly. But trust that it keeps going like that forever on the sides. So the reason for that is, the reason for that is that the Fourier series, the formula for the Fourier series, involves summing a bunch of cosine and sine terms. And they are periodic. They sort of repeat, they oscillate. So the sum of a bunch of periodic terms, and that's also going to be periodic here. That's what we're sort of noticing. All right, so let's bring it back to our example. So what's going to happen is the Fourier series for our function is going to keep repeating the shape of f of x, even outside the interval that f of x was defined on. So let's go ahead and draw a graph of this. Okay, so I'm going to draw some axes. So let's draw some axes. Okay, and then I'm going to draw the graph of the original function. So we had this x squared looking piece to the left-hand side, and a whole at negative pi, and this was negative pi comma pi squared. And then we had the horizontal line portion. So this was 0, 1, and then this horizontal line continued until we reached x equals pi. All right, so that was the graph of the original function. So with the Fourier series now, so we know that at x equals 0, the Fourier series converges to this sort of, midpoint of where these two circles are, the one above it from that piece and the one below it from the other piece. And at pi and negative pi, the Fourier series converges to the average of the y values of these two endpoints. So that was, let's say that's somewhere here and somewhere here. And what we just sort of observed from our animation was, even outside this interval, so actually first off, within the interval from negative pi to positive pi, wherever the function is continuous, the Fourier series is going to converge to where the function is exactly. So on this interval, on the parabola, the Fourier series is going to converge to where that part is, even on this line, because it's continuous everywhere there. But in the animation, we saw that, this repeats even on the outsides. So now at pi, it'll pick up at this open circle. It'll create that parabola shape until we get to 2 pi, because this distance has to match up with this distance. And now I make that line shape. And that'll go another pi distance, so 3 pi. And it'll keep going like that this way, even on the other side of negative pi. So I'll have my line shape until negative 2 pi. And then I'll start with the parabola shape until I reach negative 3 pi. And it would keep going like this. All right, so in this picture, the interval from negative pi to positive pi, that was where f of x sort of existed. F of x was sort of defined here. But our Fourier series is going to be, not only on the interval, it's sort of, repeating what happens there on the outsides. Okay, so in this problem, we want to know what happens at 5 pi over 2. What does the Fourier series converge to? So 5 pi over 2 is over here. This is 5 pi over 2. So if I want to know what 5 pi over 2 is, I'm going to use the sort of periodic nature of the Fourier series. It has a period. Period is sort of like the length of time that passes before it repeats. The period is 2 pi. Okay, so if I go back 2 pi from where 5 pi over 2 is, so if I go back 2 pi, I end up at pi over 2. So notice that the y value at 5 pi over 2 should be the same thing as what the y value was at pi over 2. So let's just state that. So I want to know what my Fourier series of my function is going to converge to at 5 pi over 2. So based off of this periodic nature of the Fourier series, at 5 pi over 2, it's going to converge to the same thing it does at pi over 2. So that's when I sort of went back this length of 2 pi. And at pi over 2, we can use our convergence theorem. It's going to be 1/2 f of the right-handed limit at pi over 2 added to the left-handed limit at pi over 2. Okay, so what are these limits? So we got 1/2. So at pi over 2, our function is continuous. So the limit is just what the value of the function is at pi over 2. And the y value there is 1. So both of these are 1. The left-handed limit and the right-handed limit as x gets close to pi over 2 are both 1. So we end up with just 1. And that's kind of what we expected. Looking at the graph, at 5 pi over 2, the y value there was 1. But this is how we justify y using the periodic nature of the Fourier series, as well as our convergence theorem.